All right, up and running. Lesson set 16. I am going to probably start with problem number 16 because I woke up this morning realizing that there's another way to look at it. And I've been doing this a long time. And so that's something to be talked about, that I don't think you can look at any one of these problems too much. I don't think it's much different than a sport. You learn how to throw a baseball and then you play the sport. You just try to keep getting better and better at it. Got to get the mechanics a little bit, but you take a martial art, you start with a kata. I don't think you stop doing that kata. You just do it better and better and better and better. And somebody who's been doing it for 20 years probably knows a whole lot more about it than the person who starts out and just trying to figure where to put their feet. Well, math's no different. Math is exactly the same. You got to get a foundation, but you never stop working with that foundation. You have to have that foundation to do more difficult problems and more different difficult skills, but it starts somewhere. All right, so looking at factoring the sum and difference of two cubes, really, let's start with 27 plus 8 again. But it dawned on me that is it any different than the problems we've been doing where we look at x minus 2 times what equals x squared plus 5x plus 7? Is it really any different than that? I don't think so. I mean, we start with the cube roots. Well, we got to get back to 27 plus 8. So let's do it. I think I need a 9 to get to 27. So I write it. Of course, if I do the foiling, I get 27 plus 18. I don't see the number 18 hanging around up there. So I got to get rid of it. Well, how do I get rid of it? Well, minus 6 times 3 gets rid of it. Yep, gets rid of it. Of course, now I've created negative 12 if I FOIL. I don't see negative 12 up there. So how do I get rid of it? Well, I know what to multiply 3 by. I think 4. And then I get positive 8, and I got to get, no, I don't have to get rid of it. That's what's there. And that tells me that 5 times 7 actually equals 35, but I'm showing it as a product. Well, can we do that for a more difficult situation? And so that we're not just memorizing a formula, but can organically get an answer here? Let's find out. I know 2 things times 3 things are 6 things. So I'm going to get 6 multiplications. And I'm hoping that I can make them come out to 2. So we need to know the cube root of 27x to the 6th. And we started with this on day 1. Day 1 of this class, we tried to define what that 3 is. And I hope you would say cube root. So what's the cube root of x to the 6th? X squared. So we've got 3x squared, and we've got minus 5y. And we want to figure out times what is going to get me 27x to the 6th minus 125y cubed. And if we're going to say equals, be nice if we were right. I know I did a mistake, and I'm getting checked, which is great. I said 3 plus 4 is 5. I feel kind of foolish saying that, but I said it. And I'll do these answer keys and 80 problems, and I'll always get a couple wrong because I'm just having to generate them quickly. It's a lot of volume, and you get talking, you make a careless error, right? But if you're doing it for a test, whoa, that's another matter. Nobody's grading me, so I'm just flying, all right, and learning from it, and hopefully keeping the noggin sharp so that at least one more year before I'm in the nursing home. All right, but if you're going to use an equal sign, it would be nice if it was true that 3 plus 4 equals 5, and it's not true. Okay. So what do I have to multiply 3x squared by to get 27x to the 6th? I hope you can see 9x to the 4th. But that gives me a problem. That gives me minus 45 x to the 4th y. Be nice if I had positive 45 x to the 4th y, so it wasn't walking around. Well, when I bring in a new term, I think I'm going to multiply it times 3x squared. So what do I need? I need to multiply 3 by 15. 3 by 15 gets me the 45. And if that's a minus, I know I need a plus. And now I need x to the fourth y, but I got x squared here. So I think I need x squared to get back to x to the fourth. And I think I need a y. Of course, that gets me new terms, right? That gets me minus 75 x squared y squared. Well, all right. What is so there's got to be a positive, right? I think I need to get rid of this. Well, how do I get rid of this term? I need to multiply 5 by something that gets me well, let's just cut to the chase because it's the first time I'm doing this. I am going to figure out that I need positive 25y cubed. Okay, so that's what I needed to do to get here, right? So to get this times this, there's my 75. Okay, so with practice, I'm seeing that more clearly. Hopefully the next time I do it, a little better explanation as well. But I also need x squared y squared. So therefore, I've got the x squared, so I need the y squared. Oh yeah, that's what it takes times that to get that. I'm done. Okay, a little awkward on my part, but hopefully there is something there that we keep our eye on and get better at. Now, how are we going to get better at it? We're going to practice, the foundational aspects of this by putting in numbers and seeing how they work. All right, now we did y equals sine x yesterday. Now we're going to look at the cosine function. And the cosine, remember, we started with a 3, 4, 5 triangle. And we called that angle A. Now I'm calling it x. We talked about that in lesson set 15. Whatever's in that parentheses, with this terminology, this nomenclature, that's an angle. And what we're trying to understand is we understand angles if they're in degree measurement. We're trying to learn a new way of looking at an angle. All right, so here's a degree measurement. We usually show that, but it's also an arc length, a section of the circumference of the circle. And if we leave the circumference of the circle, the circumference 2 pi r, if we let r be 1, then it's 6.28 times the radius length, whatever that radius length is. The walk around the circle is 6.28 times that. And if we are looking at the sine function of angle x, and we're calling it 4 over 5, well, that's the same thing as the sine of angle x equals 1 over 4/5 over 1. 4/5 divided by 1. That's the same ratio. So if I make this a unit circle where the radius is 1, then that's 4/5, and that's 3/5. That's the cosine. And the cosine becomes the width, the sine becomes the height of these angles if we're in a unit circle. All right, so width is horizontal. And if the radius is 1, and I'm at 0, 0, the center, then the widths are biggest at 1 and smallest at -1. And now I have to envision going around the circle. Okay, if I go around the circle, let's see if I can do that from the side. Not too bad, a little rotator cuff problem there. And I start looking at the next widths by drawing a perpendicular from the circumference to the x-axis. I think my width is now smaller than 1. So what does the cosine curve do? It starts at 0, no walk around. I have a width of 1. 0 gets me 1. And then I walk around the circle, 6.28 units of those units. And 1 radius length translates into 1 unit on the circumference of the circle, 1 radius length wrapped around the circumference of the circle is about 57.3 degrees. It's good to have a feeling for conversion there. Okay, and so what does the cosine curve look like? And we'll continue to have this discussion, but I got a lot of other problems to do. The cosine curve starts at 0, 1, comes back to 0, 1, 1 revolution, halfway around, there's the width, halfway around, takes me to that side of the circle, which is -1. These are widths, to 1 to -1. I'm back to 1 at 2 pi. 0 gets me 1. Therefore, pi gets me -1. and I get 1 period of a sine ensuing. 1 period. And we know a few things. Now I asked the question, the sine of 3 in the last test, which was an unfair question to expect anybody to give me an answer at that stage. But we got to start conversations. Sine of 3. Well, where's 3? I don't see a degree symbol there, so it's a radian measurement. Well, here's a circle. How many radius lengths does it take to get to 3? Well, I got a frame of reference here, 3.14. Takes me halfway around. So 3 is pretty darn close. And if I draw the triangle and perpendicular to the x-axis, notice that arc length from there to there is about the same as the vertical height of the triangle I just drew. Okay, now where is 3.14? 180 degrees. Where is 3 radius lengths? I don't know. You know, could do some real thinking, but it's a little less than 180 degrees. But I can tell you what this is approximately. Without a calculator, it's approximately 0.14. The distance between 3 to 3.14. So that question was put on the test. So you'd look at it, probably ignored it, moved on, and I don't blame you. You know, you're just starting to learn what a radian is. And very rarely do you get anybody coming out of a high school trig class that be able to tell you what a radian is. And it's central to this entire study. So we're starting to talk about it early, so we can talk about it for a long time. All right, there's my pitch. All right, probably you had some other things. Oh yeah, I want to do one more problem that is in front of us constantly. All right, so let's just say, and I'll do it as a sine and a cosine function. All right, so here we go. I'm about 68 inches high. Maybe that's 56. We'll call it 56. Okay, so I'm going to start here and I'm going to go woo, woo. Didn't mean to have the break there. Okay, but I think I did 3.5 revolutions. 3.5 patterns. 2, 3.5. Wait a minute, I started here. 1, 2, 3, down. Okay, so my height is 68. I'm at a max. I did woo, woo. 1 revolution, 2, 3.5. All right, and let's give these some years. So let's say that I got 68 of something back in the year 1350. I had a lot of friends back then. And let's go up 100 years to 1450, so we keep the math simple. And I think I said I went down to 56. Well, I need a frame of reference to measure. Ooh, I think it's my nose. Yeah. Okay, so I think we need that. And so what's between 68 and 56? Counting on my fingers, 62, I think. 4 and 2 is 6. 6 as well. I'm confident that's correct. We'll do it as a sine function. Let's unwrap the circumference of the circle. Right, let's unwrap it. If we unwrap it and we put it on, oh, there goes the right knee. Okay, that's why I fall. That's how I bang my head. Losing the strength in the right leg. Too much soccer over the years. So let's just write it. See if you can follow it a little bit better. I've got to turn 1350 into this place on the circle for a sine function. That's pi over 2. Okay, so x minus 1350 gets me pi over 2. Okay, so I'm here. What's the maximum height? 1. Okay, well, I got to turn the number 1 into, from 62 to 68, I got to make that a 6. So I'm going to do 6 times the sine function. Now I got 6 units. 6 units doesn't take me to 68 unless I add 62. Now it does. And of course I went 1 pi, 2 pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Well, that's how much further along I am down the circumference of the circle. And it only took me 100 years. Wow. Wow. So, geez, it's how many, how many inches is that? 68 to 56, 12 inches, 24 inches, so on and so forth. It only took me 100 years to take that journey. Isn't that nice? Now, cosine function, we got to figure out where the cosine function's a max. And I think widths are a max at 0. So we'll change sine to cosine. We'll change pi over 2 to 0, which you don't have to write. And that's that function. There's a lot of ways to write those functions. Let's keep going. Got some things I got to get done before 10 o'clock. I better get a move on here. This hopefully is starting to come into focus. All right. I asked you to graph this. And I hope you're seeing 3x times x. I'm hoping you're seeing 3x squared and know, well, I know that's the shape. And we talked about letting y equal 0. I think we're trying to solve those problems. So I think I see a -9 gets me 0. And I think I see a 1 gets me 0. I hope you see how a 1 gets you 0. It's either this parentheses has to equal 0 or this parentheses could equal 0. So I hope it's not, going to be hard finding those numbers. And therefore, the most important place is in between -9 and 1, which I think is -4. I'm counting on my fingers properly. And why don't I plug -4 in now? -12 minus 3 is -15. -4 plus 9 is 5. There's a nice 3-to-1 ratio there. Probably has something to do with that. -75. Okay, so now I already got my roots, right? But I certainly could have gotten my roots by looking at what? The A term. -4 gets me -70. This is another problem on the test, right? And the A term is what? We said it was 3. Well, looking at this, I know I'm measuring my x values from -4. I know I have to go up 75 units up to get to 0. So therefore, I'm going to take the square root of 75 and I'm going to divide it by 3. That's what the graphing form would have been. We can find 3 minus 75 to 0 is 75 units of change. The squared change from -4 to 1 is 25. There's your 3. So we could have found that. Let's see if this gets us -9 and 1. I hope it does. -4 plus minus 25, right? That's 25, so that becomes 5. And what's -4 minus 5? Oh yeah, from a different perspective. -4 plus 5. Yes, from a different perspective. And where are we headed? We're headed to inequalities, not where it equals 0, but when am I greater than 0? Well, I think I could look on a number line here and put my roots, which are 1 and -9, and I think I could trial and error this by plugging in a number bigger than 1. How about I throw in 100? Well, that's roughly 300 times 100. I think that's bigger than 1. I think that's true. Oh, yes, all these y values, right? If this is a number line, it's these x values here that are giving me things bigger than 0. I think all these x values are getting me things less than 0. So let's put 0 in, and we get -27 greater than 0. I think that's false. And it's going to turn out to be true on this side. If you pick a number like -100, you go ahead. You have to do the math to show you that it's true. And we're starting to learn interval notation. So -infinity to -9, parentheses, union, also the interval 1 to infinity works. Those are the numbers that make this true. Okay, and we're going to start adding more terms. But right now, that's enough. And now if I wanted it or equal to, let's get rid of that term, then this becomes a bracket, and this becomes a bracket, which means that that's true, and that's true. In interval notation, it's a lot easier than writing x less than -9 and x greater than 1. And why is it better than that? Because that's not true. You cannot be a number that is 2 places on the number line at the same time. I can't be less than -9 and bigger than 1. I'll keep trying. I don't think it's going to happen. And that was something you probably discussed, conjunctions and disjunctions. What's my function? Probably had that conversation. Right? But interval notation makes it a lot easier to talk about intervals. That's why somebody probably invented it. the ln of x minus 2. Well, lesson set 15, we established some values. So now we want to graph this. I know the ln of 5 is 1.6. So why don't I pick a 5? Oh, no, I don't think I want to pick a 5. I think I want to pick a 7. Because I'm doing 7 minus 2. So this is now 7. And it gets me 1.6, roughly. Let's make that bigger. Let's make that 1.6. And I know that 3 gets me 1.1. So I want 3. Oh, no, I think I better pick a 5. I think I better pick a 5. So why don't we call this 2 units of change? There's 2 units of change. Yeah, we'll go with that. We'll go with it. And I get 1.6. 1.1. That's my best guess. That's my best guesstimate. Maybe a little higher. So that's 0.5, 1.5. Good, close enough. Close enough. All right. So 1.1. I think 2 gets me 0.7. So I think I get the hang of this now. I think I need the number 4, which is halfway from that to that. And that's 0.7, which is maybe here. Yeah. And I know that a 1 gets me a 0. So I think I got a 2 here. 2. So I need 1, so I need the number 3. That gets me a 0. Oh, I think I'm seeing this, that part of the graph. And I know that the ln of 0 is undefined. ln of 0 is undefined. I'll use null set. Okay, it's undefined. I should write undefined. Undefined. How about I leave it there? Okay. Well, that's why I start making a bracket here. At x equals 2. Hope you can see everything. Renee, center this. Thank you. And then we have what? Numbers like a half and a third and a fifth. Well, they seem to be heading, this column seems to be heading towards 0. And if I put 2 in here, right, then I think I'm really looking at 2.5 and 2 1/3 and 2 1/4 and 2 1/5. And each time I'm going to get the same mirror image. And I hope we start to get a little better sense of what's happening that section of the graph. So how do I graph the ln of x minus 2? Well, I see x equals 2. I know that's my asymptote. I know the general shape. I know the ln of 1 is 0. So I'm going to put the number 3 in to get 0. And I know the ln of 3 is 1.1. So I'm going to pick a 5. And I know that's 1 unit of change. And well, we'll look at that in a second. So I'm going to pick a 5, and that's going to get me roughly 1.1. That's an approximation. All right, it's good enough. It's good enough for us, for right now. So we got another logarithm. Pretty darn same as the last one. Remember, ln of x is replicating 2.71 to the x. And we're doing x minus 2 here, right? So we're doing x minus 2. So this is a very similar graph. So I'm going to cut to the chase. I'm going to go x equals 2. I know it looks like that. I know if I put a 3 in, I get the log base 3 of 1 is 0, right? If I multiply that times something, it means I'm multiplying this times something. That's an easy multiplication. So that's a nice pick. And so a 3 gets me a 0. And now I think a 5 is even easier to see what I get. I think log base 3 of 5 minus 2, I think that's a 1. I think log base 3 of 3 equals a 1. So what do? We set the parentheses to 0. It got us our asymptote. We set the parentheses to 1. It gave us an easy calculation. And we set the parentheses to the base. This is a base 3 log. It would be nice if this was a 3. And I hope you can see what happens if I make it a 9. And I hope you can see what happens if I make it a 1/9. When I make it fractional, I'm heading down to negative infinity. And when I push the exponents to the right, I'm getting slow. Each quantity is getting me a little bigger exponent. All right, enough said there. Now we're looking at e to the x minus 3 plus 1. We're going to keep each lesson set's going to make these more complicated. And I hope you can look at the table values here and make some connections. Over there, the ln of 2 was approximately 0.7. Here, e to the 0.7 equals approximately 2. Starting to get a feel for inverses here, I hope, because this is dyslexic stuff. But we got to work with it, got to work with some numbers. So the inverse had a vertical asymptote. Its inverse has a horizontal. And that looks like a constant to me. That looks like a constant. I'm at the same height. Number 50, what was I, 56 here? All right, well, I see a constant. I see a constant of 1. And I know the inverse looks like this. So I'm going to make e to the 0, which gets me 1. And I'm going to work with e to the 1.1, which gets me 3, approximately. Right? So I'm going to get a 3-to-1 ratio. There's 1 unit. There's 3 units. If I put a 0 in here, well, I got to pick a 4. No, I got to pick a 3, excuse me. All right, so I need a 3 to get e to the 0, which is 1 plus 1 is 2. And I can now see that I went up 1 unit, which happens to be the multiplier here. That was my first jump. That's going to change in future work we do. All right, but now if I pick a 6, well, I think I'm 3 times that one. 6 minus 3, I'm sorry, I botched that. I told you it's dyslexic. I need 4.1. Right? 4.1 is going to get me 1.1. And what's e to the 1.1? 3 times this. And 3 plus 1 is 4. So 4.1 is roughly getting me 4. And if I had a negative 1.1, right, then I'm really getting something close to a third. So I'm not tripling. 1/3 over here of that. And if I keep going in the negative direction, this disappears and the graph goes to a height of 1. Because I could make this the number 1/9. I could make it 1/27. I could make it 1/81. And if you're multiplying, that multiplier is getting smaller and smaller and smaller. It's disappearing, heading to the constant. Okay, we're just continuing conversations here. So all we're doing. I probably should have done this one first before I did e to the x, but I want to make sure that people are seeing every problem. So that's why we're doing the reverse order. You can make a lot of gains provided you talk about something for 20, for a minute or 2 each day. The more things you talk about, the more topics you talk about, the quicker you're going to build your foundation. So I see E was 2.71, and I had x minus 3 over here. Now we have x minus 6 plus 1. But it sure looks like I've got a similar situation. And I got y equals 1 for the same reason we did over there. And I'm going to let x equal 6. And I'm going to let x equal 7. Okay, if I put a 6 in, I get 3 to the 0 plus 1. So if I put a 6 in, I'm getting 2 units out, which is a jump of 1, which is the number in front of 3. Okay, so I get 2. When I plug in a 7, 7 minus 6, 3 to the 1 is 3. I get a jump of 3 on top of 1, which takes me to 4. And we're going to standardize our exponential work to always be a 3-to-1 ratio. Except for when the base is something other than 3 of a regular log. So I'm having a heck of a time today. Time for more sleep for this guy. All right. Well, here's a square root function right here. And what do I see? I see the smallest a square root can be, right? I can make that square smaller. I can make that square smaller, that square smaller. I think it's 0. So the square root of 0 is 0. The square root of 1 is 1. So I'm using a little dot there. The square root of 4 is 2. Well, 4 is a bigger jump. From 1 to 4 is a jump of 3. From 0 to 1 is a jump of 1. That's a jump of 1. That's a jump of 3. Next jump is going to be a jump of 5, so on and so forth. And I'm going up by 1 with bigger and bigger jumps. I get something that looks like this. All right? And it sure looks like the most important is 0. Square root of 0 gets you 0. So I want the square root of 0 to come out of that. And I hope you can see that -5 makes it happen. So -5, -3 is this place on the curve. I'm going up twice as fast as this one, so I'll go up a little faster, a little steeper. And I got to get something to match up. So what did we say? 9 gets us 3. So what makes this 9? 4. That gets me 3 times 2 is 6. 6 minus 3 is 3. So why don't we call this 4, comma, what did we say? 3. That's on there. Well, there's a whole bunch of places on here. I'm a big fan of the square root of 25, so I'm going to pick 20. I'm going to pick 20, which is 9 units. I need another 16 units. I'm way out here. I'm further out than this, but we're going to call that 20 because I'm running out of room. And if I do, I get 10 minus 3, I get 7 units. I'm getting slow growth. That's what it is. Yesterday, we talked about taking the absolute value of x. What happens when you take the absolute value of x? You get a sign change. Well, what do I have in here? I've got a different linear function. I got 3x minus 3. Well, y-intercept's -3. X-intercept is what makes it 0. In this case, that's 1. I've got that line. What happens when I slap an absolute value on that line? All the negatives become positive. And so what's the most important number? 1. And if you let x equal 1 and you plug it in there, I hope you see the absolute value is 0. Smallest distance you can travel is don't travel at all. An absolute value measures distance from 0 on a number line. What's the shortest distance I can travel from here? Stay put. So what makes stay put? X equals 1. So there's a 1. That makes that 0. That makes that 4. Very similar to the quadratic. But we have linear branches. Now, I'm a big fan of crossing the y-axis at the right place. So I'm going to let x equal 0, and I'm going to do the math, and I know 0 is to the left of 1. The absolute value of -3 is 3 times 2 is 6 plus 4 is 10. That means that if a 0 gets me 10, then over here, a 2 is also going to get me 10. Let's put a 2 in. 6 minus 3 is 3. The absolute value of 3 is 3 times 2 is 6 plus 4 is 10. And then I'm going to add 4. Well, I've already added 4, right? I did it in the process there. So here's your x-axis. Here's your origin, right? If you want to put x, y-axis in. Here's your graph. All right. We'll keep working with that. Not talking about those as much because people are starting to see those clearly, I hope. What do we got? We got a quadratic. First thing you should do is look at the sign of the coefficient. It's a negative. So we have a cup shape down. We look for minus b over 2a to get this x value. So minus b, 12 divided by -4, that is a -3. That tells me my y-intercept is on this side, and I can just take it. And now I'll plug -3 in. And if we don't get a 2-to-1 ratio opposite, we made a mistake. -3 squared is 9, minus 18. If the next number isn't positive 36, we've done poorly. Oh, minus 3 times. We're good. We add 7. When you add the first 2 terms, you get, I don't need the plus sign, but you get half of this. 18 plus 7 is 25. And we're now done. And if I know -3, 0, then -6 should also get me 7. And if I want some other number, let's say I want to know when this thing hits a height of minus 101. Minus 1, I know they exist. I know they exist. And they are the following answers. So when does this hit? Well, I've got to measure from -3. And I know I got to go over this way and that way to get to an x. To get to an x, that gets me this number. And how do I get from 25 to minus 101? I think I got to go down 126 units. But if I'm tripling it, doubling -2, then That are real, all right, negative and a negative. And those are the numbers that make me hit minus 101. Okay, I'm hoping you see the coordinate 5, -2, because if you do, you get 0 equals 0, and that's the point slope. Look at this. I'm a big fan of making the positive 2 over here, making it -2, and then I can see the coordinate 5, -2, we'll call that 5, -2 right there. And I'm going up. At what rate? Over 4 and up 3. That's about right. Over 4 from 5 is the coordinate 9, and up 3 from -2 is the coordinate 1. Does it look okay? I hope so. 3x plus 5y equals 30. Yes, it's important to be able to see the following. 0 gets me 6, and 0 gets me 10. Really important to see that, because pretty soon we're going to be graphing these things. X squared over 2, 9, plus y plus 3 squared over 25 equals 1. There's a similarity here to that, because I can make this 0 by plugging in a 2. If I plug in a 2, I can see that a 2 works, because this is gone, and something else works. Maybe you can spot it. -8 also works. So where's 2, 2, -8? Let's go up 2 over 2. Let's call that 2, 2. Let's do 2, -8. That might be here. Okay. And I could have done the same thing with -3, -3. That would have erased that. -3, that's gone. I think I'm looking at 11. 11 minus 2. No, I need 3, right? I'm looking at a 5. And I'm also looking at a -1. -3, -1's here. -3, 5. I should have labeled some things. Let's label the center of this. Let's actually just not even do it on an XY axis and just see these things. I think the center of this, I gotta start again. So it's vertical, it's one of these, right? Boy, is that one line. All right, I think the center is 2, -3. And I think I got the coordinates -3, -1. And I think I got the coordinates -3, 5. And I asked the question, how far is it from -3 to 5? I made a mistake here. I want to travel 5 units from -3, 5 units from -3. 5 units from -3 is 2. Right? And if I go 5 units up, that hasn't changed, but this is 2 gets me what? +2. There we go. So I botched that. You know, it's at the end of the video, you watch me fall apart. Just like what? Who fell apart? The Wicked Witch of the West. Right down on the floor. All right. So anyway, we're going to be looking at ellipses and creating zeros, right? Started a long time ago. Put a 0 in, see a 6. Well, now you got to make zeros. Right? The level of difficulty goes up a little bit. But if you're spotting how to do this, if you know how to do that, it's just a little jump. Yeah, you can make it. All right, I'm rambling. Anything else to say? Oh yeah, keep the jokes coming, Yasser. You got me good this morning. You can tell I'm tired. I actually went to the video and looked to see what mistake I made. I figured I just made a careless mistake, but you got to be able to laugh at yourself. I do that all the time. And I have good reason to laugh at myself. All right. Hope everybody's good out there. As the Asher said one time, stay safe and warm. We got another big storm coming. Although they're not big anymore. Oh my God, they're not anything like 1993. I think Boston got, what, 60 inches of snow on Route 128? It was one of those dates. All right, ciao, ciao.